speaker coming up right now was formerly the founder and CTO of Full Contact. He is a Techstars alumnus with 16 years of experience. Please welcome the CEO of AgilData, Dan Lynn.
Hi guys. Thanks. So I want to talk to you guys about data analytics today, and specifically this thing we've all been chasing. I'm a big Monty Python fan, so I figured I'd dig out some Monty Python references of the Holy Grail here. But as database practitioners, we're chasing this nirvana of balancing operational data stores with analytic data stores. And that's what ETL pipelines are all about. That's what data warehousing is all about. And it's a lot of work. And we have a lot of people on those teams. And I think there's something that has arrived that can save us from this pain. So a little bit about me, a little bit about my company. My company's called AgilData. We're loosely based all over, actually. I live in Colorado, although our team is spread out over 6 states. We primarily help people build data pipelines. We help you build out your data strategy in an organization. We do a lot of data integration, BI, analytics. We help you modernize a data infrastructure if you're trying to bring it from an old school, really complicated ETL process to something a little more modern. And then we'll help you wrap APIs and applications around that. Another thing that we got to do is we got to help people scale out MySQL-based architectures. So we have a product that is actually handling all of the user database, for instance, on the new Pokemon Go launch. Not the rest of the system, but the but that's based on MySQL, and that's a pretty large cluster of MySQL servers, larger than you probably would otherwise expect MySQL could do. We also have a free MySQL performance analyzer that you can get off our website. It's pretty cool. You download it, it'll sniff all the traffic on your database. It's based in Rust. It's open source, so it's going to sniff your traffic, so you better look at the source code. And then it'll actually ship that up for analysis. We'll tell you kind of any performance bottlenecks, stuff like that. One last final plug. I'm also organizing a conference in Colorado in November 10th and 11th. It's the Rocky Mountain DataCon. That's focused on data science, data engineering, and data DevOps. So everything data, located in beautiful Denver, Colorado. I invite you guys to come out to that. It's RockyMountainDataCon.com. You can search for it. I think Google's found it by now. So let's talk about the trade-offs that we have to make as data architects. We're constantly fighting this battle where you're optimizing for user experience on one end, and you're optimizing for business intelligence on the other end. And earlier on in an application's lifecycle or an application launch, user experience is critical. If you don't have users on something, there's no point in doing the analytics. So earlier on in a lifecycle, it's very simple to focus on an operational data store that's going to give you what you want. Later, you're going to need to add in analytics on that, so you can optimize how are you treating your users, what is the flow for those users, how are we making money, is this a profitable business or not. So what I want to talk about is this fight between transactional processing and analytical processing, and see if there's a way we can kind of bridge the gap. So first off, I want to talk about what is OLTP and what is OLAP. Let me actually see who knows those acronyms, right? Okay, cool. Okay, that's actually a pretty good distribution. So I'm going to explain them. So OLTP is short for Online Transactional Processing. What it means is the database is optimized for low latency access to the current data of the application. It's the hot data. It's the users. It's the records. It's the orders in the e-commerce system. There's short transactions. You're inserting a new record. You're updating something. You're deleting something. There's high concurrency. There's lots of users. As we saw, a lot of systems like Couchbase, for instance, are focused on operational data stores, where you're trying to get tens of thousands of concurrent users on the same system. Examples in this are you're putting an item in your shopping cart, right? You're resetting your password. These are short transactions that mutate the state of the database on kind of a per user, high frequency, high concurrency basis. So the simple acronym for this is Online Transactional Processing, OLTP. You'll see that used all over the place. the actual data store, the schema that you're using, if you're using one, is optimized for the aggregation of historical or bulk data. What that means is that the aggregation, and when I say aggregation, I mean functions like mean, average, sum, count, that kind of stuff, can span millions or billions of records depending upon the size of the data. Right? It's lower concurrency typically because it's serving some analysts within the company, typically I should say. When you scan those millions or billions of columns, I gave something away, millions and billions of records, you're actually usually interested in fewer columns than the entire record, and that's a key point. So an example of this is like, what's our average shopping cart size grouped by week and maybe the affiliate that gave us that lead? And you're trying to figure out some analytics, which of our affiliates are our best relationships, and should we invest more in? What are the top 5 paths that our users take through our website that ultimately lead in purchasing something, for instance? So to optimize for these two different use cases, transactional and operational stores are focused on reading or updating an entire row. Right? So you have the whole row, the whole customer record. Right? You're reading to the disk, writing the disk on a row-by-row basis. You're getting the whole thing, all the bytes off of it, pulling them into memory, doing something with them, and then maybe updating portions of that. The indexes that are in like a transactional store are used to construct like a full business object. So if you have customers and orders and line items and stuff like that, you might join a couple different tables to construct like the record you want to work with at that point in time. In the world of Hadoop and in the NoSQL world, they generally behave the same in terms of disk access performance, in terms of storing an entire row or entire record. Like if you have a document, there's actually some pretty cool tricks in the different NoSQL stores that will actually write partial documents and things like that. Typically, in these sorts of stores, the scan performance is limited, and there's a very specific reason for that. If you read the whole row and you only care about the order quantity column, you're going to have to read the whole row for every object and throw it out. Right? So OLAP data stores or analytical data stores try to fight that problem, and they do that by optimizing to aggregate for specific columns. And the way they do that is they actually store the column on a per column basis. So rather than per row basis, you have columns that are just contiguous. And the sequential access, which is the fastest way even SSD can read, can just scan right through that very quickly. So in this case, if you want only the unit price column and the quantity column, that's the only thing you need to ask the I/O to get for you. So by laying it out on a per column basis, you don't have to like read data and then throw it out, which is really good for scans. But if you want to read specific rows, right, you want this column, that row, this column, that row, it's not so good because you're doing a lot of random I/O, you're doing a lot of page faults, all sorts of stuff like that. And it's really hard for random updates because if you take a whole row, every time you change the user record, if you were to take every one of the columns in the user and write them out on the disk into one stripe, if you change that user, you might have to change tons of different columns that are stored out in different areas of the disk. So the update performance on that is slower. And that leads to batch processing for batch analytics. So Hadoop optimizes for OLAP basically in the same way. Right? I think I saw a few hands come up earlier with people that are familiar with use Hadoop. How many are actually using Hadoop? Okay, cool. So good targeting, I think. So Hadoop is like the big data OLAP system. Right? They didn't use that term, but that was the whole point of it, was to crunch massive data and to do it in a cost-efficient way by leveraging these non-super expensive server systems, right? Using clusters of commodity hardware. And so there's this thing in Hadoop called HDFS, which is the Hadoop Distributed File System. And it splits up the data that you're storing, which could be CSV data, it could be raw data, it could be JSON data. Splits it up into chunks of 64 megabytes, usually, sometimes bigger. And then it takes those, and they're called a block, and it spreads them out all over the cluster. Right? This might be thousands of nodes for a significant size of data, or it just might be 10 or even fewer. And the key innovation here is to take the query, serialize it, ship it out to every one of the machines in the cluster, and have them compute partial aggregates on all the machines in the cluster. And then pull back those partial aggregates to one place, right, where you're shipping far less data over the network. You're filtering far less data in the application, and leveraging the CPUs and disks and memory of dozens of machines. Along the way, they developed these new data formats, the most exciting of which recently is this thing called Parquet. And Parquet is a columnar data store format based off of the Google Dremel paper that takes complex objects. So think a whole JSON document that you might stick in Mongo, right? Lots of different things within that document. And it can break it down so it's optimized for columnar storage, aligning on disk per column basis. The problem is, as I mentioned, is that updates are also very expensive for two reasons. One is because you would have to recompute the whole column, and two is because HDFS is an append-only file system. So you would have to basically rebuild that entire 64 megabyte block, even if you just changed the password of the user. So it's not an operational data store. It's not designed for that. So we have a fight. Right? We're trying to balance between scan performance on one end for analytics and updatability for user experience on the other end. And the common way of putting this together is this thing that came out called the Lambda architecture. The Lambda architecture, I think, was originally proposed by this guy named Nathan Mars, who made an Apache project called Storm that came out of Twitter. And here's roughly how it works. If you imagine you have a whole bunch of data events coming in, right? Clicks on a website, financial data, things that are happening, and you need to do analytics on them. The very first thing that you would do in a Lambda architecture, and it doesn't have to be Hadoop, but it typically is to write this to HDFS, or to write this to your append-only file store. Then you do some sort of batch computation on that. So you're either running Hadoop's MapReduce, or you're running Apache Spark against that, or in a more traditional data warehouse, you are doing batch analytics against your read replica of your transactional store. They're computing these views, these batch views, possibly shuffling things around, possibly re-indexing them, making a star schema perhaps, and then sticking that into something called, like in the abstract, a serving layer, right? Which is either like it could be MySQL, it could be Oracle, it could be SQL Server, it could be Postgres, or in the NoSQL world, it would be something like HBase if you're a Hadoop member, but it could be any of the NoSQL stores as well. The problem with this is you're limited to how quickly you can do that batch computation, right? What's the latency of that? So your data is always only as fresh as your last compute cycle, which is a traditional problem in data warehouses. It's like, 24 hours old, or 1 hour old, or however fast you can do that. So the Lambda architecture proposes this other layer where you send the same events into some sort of a queue. The most exciting queue these days is Apache Kafka, but there's tons of choices. And then you have some sort of speed computation layer. Something like Apache Storm, where there's a new one out called Heron, there's a new one out called Flink. Apache Spark has a streaming component, which is mostly streaming. It's like on 1 second intervals, but it's fairly robust these days. And then you actually compute these real-time views, stick them in possibly that same data store, the same MySQL serving layer data store, and then your query layer merges the batch computation with the thin veneer of more up-to-date results. So this Lambda architecture gets you this fresh data without sacrificing the usability of having a highest performance operational data store on the front end. The problem is it's pretty complex. This is the simplest I could possibly describe this thing. I think I just described probably 3 or 4 different operational systems. Your operations team has to keep running. Each of these is a distributed system in many cases, so it's not just like one machine. You might have just described 24 machines here or more. So I think there's something cool that just came out that might simplify this. And it came out of a company called Cloudera, I think, who you guys heard of earlier. There's this thing called Apache Kudu. It's very new, it's very young. I'm hoping to just tell you guys about it, get you excited, and we can talk more about it afterwards. I'll be hanging out by the booths right after this. So it's all the way up to version 0.7 right now, which which in open source terms sometimes means relatively mature. That said, they're targeting a 1.0 release later this year. We at AgilData are very involved with Kudu. We're doing a lot of performance testing. We've done a lot of work with it with at least one large customer now. And we're very excited about where this could go. I kind of want to tell you a little bit about how it showed up and what problems it's trying to address. The design goals here for Kudu is to bridge the gap between the operational data store that can accept updates and the analytical data store that can aggregate over columns very quickly. And then this is, I borrowed this slide from Cloudera, but in their world, the world of Hadoop, it bridges the gap between HDFS, which is analytical and Parquet, and HBase on the other hand, which is operational, fast, row-oriented. And it sits in the middle, and it's a very, very fast system, almost as fast as Parquet on HDFS, but it still allows you to do updates and keep those in sync. And it does those with a very simple distribution mechanism that doesn't require a whole bunch of operational maintenance. It uses a protocol for distributed consensus called the Raft protocol, which has survived several tests at least from distributed systems testing people like Kyle Kingsbury. We're hoping from the Kudu project that we can later do one of the Jetson tests in order to really prove that this survives network partitions, which is the bane of every distributed system, is when your servers can't talk to each other. But what's cool about Kudu is rather than have like a pure NoSQL environment, there's a relational data model, so it can support SQL operations. Now it's important to know that Kudu doesn't support SQL by itself. It's not a SQL engine, it's just a data store. So it requires a SQL layer on top of it. There's several choices these days. There's this thing that came out of Cloudera called Impala, which is a SQL engine that can run against unstructured data or structured data. And so it works very well with Kudu. Apache Spark and Spark SQL work really well with this as well. So the use cases for Kudu, which I think are really cool, is my favorite one is what I would call online reporting. And what that is when you have customer-facing analytics. So in an application where the users of the application have users themselves or have lots of data themselves, an application has to offer analytics and reporting to its own users. I think anybody that uses Google Analytics is a pretty key example, where you have each user is dealing with thousands or millions or more data points themselves. And the whole point of the application is to offer analytics in many cases. Or anytime you're dealing with transaction, meaning like financial transactions, you're trying to aggregate that and offer those sorts of dashboards and real-time dashboards to users. Users are very impatient people. I'm one of them. If I change a record within the application, I want the total count of whatever, or the total sum of whatever, to reflect that right away. I'm not going to wait around for your batch process to come around an hour later and tell me that my new sum is available. So the workload for this is that you're doing a lot of inserts, because users are adding things, they're updating existing records, meaning you have to mutate stuff that's already on disk. You're doing lots of scans for analytics, and you're doing random lookups. Kudu is a store that can actually work very well for this. For time series analytics, it's actually really interesting because it can handle insert performance fairly well. There's other systems that can go faster than Kudu for inserts, but this can scale up fairly well. When you're trying to do a continuous stream of things that are happening, you're trying to do pattern matching, pattern analytics on this, right? Like, is this user behavior potentially fraudulent, that sort of stuff. An interesting use case for this is as a message queue, it's mutable. Many times you take a message off a queue, but you don't want to really take it off until you're sure that you've processed it and you acknowledge the message. Well, if you do that with things like Kafka, that's the consumer's responsibility to figure that out. With something like Amazon SQS, which is a very nice hosted queuing system, this actually works. If that server happens to crash its processing the message that came off of the queue, it'll time out, and then another thing will pick it up. So from a distributed systems perspective, where things break, they can't talk to each other, it's a very fragile ecosystem. You need to be able to support that, and many things have difficulty with that, especially like in a Kafka ecosystem, it's the consumer's responsibility. This would allow you to make it the server's responsibility to do these sorts of timeouts, where you basically mutate the record to say, hey, I have a hold on this, I'm trying to process it, and then you mutate it again later when you comes out of machines themselves. Log and analytics, website traffic, that sort of stuff. It's kind of a very similar type of workload. But if you're running a cluster of potentially hundreds of machines, you can't just SSH into one of those machines and tail the logs. It's just not possible, right? So there's a ton of systems out there that have grown up to solve this use case, where dozens or hundreds or thousands of machines are sending all of their metrics, their statistics, their logs, and you're having to pull those in and do analytics on those. Like, what's our latency? Why is it slow when there's 1,000 machines? How are you going to answer that question? Why is my application slow? Is it the web app server? Is it servers? Is it one portion of the database? Is something locked or waiting on something? In order to actually debug that, you need to have very good intelligence into that network of machines you have. And they're sending a lot of data, so you can't just send all that sort of stuff to like one MySQL database and hope it's going to work, because you might be dealing with millions of events per second that come out of that cluster. So you need a scale-out architecture that can handle that. And you need to be able to provide random lookups when you want to look at that one particular stack trace on that one particular machine. Quick plug for the product that actually works really well in this case. Elasticsearch is actually really nice for this. You send machine logs to Elasticsearch. It's actually really good for digging in, figuring out what's going on. It's not so good for kind of the analytical side, but when you're looking at each individual component, Elasticsearch is a fantastic choice. On the analytical component, there's another thing called Graphite, which I happen to like quite a bit. It's fully open source. It's compatible with CollectD and StatsD and all those different things will collect data. And they'll pull those in. You could kind of blend the two of those with something like Kudu as a data store. Hasn't happened yet, but I'm hoping it will. So what I'm excited about going forward, I see Eric coming up. He's probably going to tell me I'm out of time. Cool. I'm excited where Kudu is. Kudu's early. We're using it with customer right now. It's very exciting. Where I think this can go is it can allow us to do reactive processing with a simpler architecture. So we don't have to have this big crazy storm cluster reading from this different message queuing system and all this sort of stuff. I see Kudu as a very fantastic, because of its Raft protocol underneath the covers, I think there's a tremendous opportunity to use this to build simpler systems that can do more impressive reactive processing to detect changes to state and send emails, things like that. We'll be able to do windowed aggregations, that sort of thing. Potentially with just one technology that's the data store and the processing engine. What I think, and this is one of the things that we're really excited about at AgilData, and I'd like to talk to you guys about this if this is interesting to you. One of the things that we've always been excited about is being able to analyze queries as they come into an analytical data store and intelligently re-index the data in response to those queries without asking a DBA or sysadmin to do it. And be able to understand, okay, the data is currently structured like this, it's optimized for this access pattern. Oh, here's a new access pattern. The machine has noticed that. We can now intelligently reformat that data, creating a materialized view that, because of the Raft protocol in Kudu, is automatically kept up to date as well, so that the new access pattern is supported. And the only thing you trade off here is disk space, right? So you use some more disk space, use a little bit of additional incremental processing on some of the spaces in order to provide dynamic indexes on data in response to new access patterns. I'm very excited to see how that goes. We haven't built this at all, so I want to talk to you guys from an ideation perspective. But please come hunt me down in the booths afterward. It'd be fun to talk. And then, as I mentioned, like, you could do a high-performance mutable message queue on this, which I think is pretty cool. Kafka is a very cool technology, and it's take Apache Kafka, K-A-F-K-A. It's taken the kind of the really high throughput message queuing world by storm. No pun intended. But it is complicated to put together. The lowest level API is addressing byte offsets on a distributed transaction log. And you have a slightly better API, which is a message-oriented API. But it's still, each consumer, you have to write some pretty complicated code to actually get value out of it. And I think you could provide some really simple, nicer APIs on top of this that provide even more value in terms of mutating messages, acknowledging them, reacting to them, all sorts of cool things. So I think I'm now out of time. I got a couple links for you guys. Take photos here. Oh, I've got some time for questions. And I
hook you up.
But it's AgilData.com without the E. And then here's my email address if you want to get in touch with me. So I can take a couple questions now. I think I saw the 5-minute sign come up. It's not standing by with the hook too quickly. And we can chat afterwards as well. Any questions? That looks like a no.
Yeah.
Just a quick question. First of all, thanks for a great presentation. I'm wondering, we've all been trying to get to that, holy grail for many, many years. How far do you think we are now that we have kudos and, we have some of those?
That's a good question. The question is how far are we to this holy grail of analytics versus transactions? In terms of implemented systems in production based on something like this, I think we have a long way to go. The Lambda architecture has got many organizations very close, right? So they're pretty close to it. Although the trade-off there is that you have a fairly complicated operational infrastructure. I think Kudu has the potential to simplify that greatly, and I think if I kind of track the way this will get implemented over the next, I want to say 3 to 5 years, we'll probably see this influence more and more technologies and see more and more stacks simplify as a result. Thanks. I think I saw one other hand. Nope.
Thank you very much, Dan and Lynn. We are going to take a 10-minute break, and then afterwards we are going to have the creator of MySQL and MariaDB speak. We will resume at exactly 11:30, not a minute later, so please be back here. Thank you.